Okay, so hope am I audible? So hello everyone, I am Subrata Samanta. So I am from IIT Kanpur. So I am one of the TA for the thermal physics course that is taken by Professor Demmala Banerjee. So today in this session, I will discuss the problem of assignment 9. Okay, so basically I solve previous year problems. Okay, and hope at the end we are able to solve this year uh, assignment 9 problems, right? So if you have any questions from the previous week, you can ask now. Okay, so don't hesitate to ask any questions from the previous week or the week content if you have any. Okay, or any doubts on the assignment to solve the problems. Okay, so you can also ask. Okay, so you can also write up in the chat. Okay, so in the meantime, I bring out my screen. So screen share. Okay, so hope my screen is visible now, right? Okay, so it seems like there is no question, so I'll start to solve the problems. Okay, of assignment 9 is one by one, right? So in the meantime, if you have any questions, so please stop, okay, and ask your questions. Okay? Or you unmute yourselves, okay, and ask your questions if you have any. Okay, so in the first problem, so the problem number 1. Okay, so let first so two globes contain 2 mole of oxygen and 3 mole of hydrogen, right, at gas at same temperature. Okay, a valve connecting the two globes is opened and the gases are allowed to mix without any reaction, right, and calculate the change in entropy, okay, given R equals to this. Okay, so how to calculate this? So basically the problem is that, so let's say we have a one box, okay, that is A, and another box is B, okay, are the two globes. Okay, so they contain, so the A globes, okay, it contain 2 mole of oxygen, so 2 mole of O2, and this is basically 3 mole of hydrogen gas H2, right, and both are same temperature T, and this is also T. Okay. So a valve connecting the two globes, so there is a, let's say, valve, okay, and this valve is two globes is opened, so we open this valve. Okay, so now they basically mix, right, so the gas in the, I think, box 1 and the gas in the container 2, container B, are basically allowed to mix, okay, right, without any reactions. Okay, so there is no reactions, just allowed to mix, okay, and calculate the change in entropy. So this is the, we have to calculate the change in entropy, right? So initial, what is the values of the entropy? So the change in entropy basically, so change in entropy basically delta S is S final minus S initial. Okay, I need to calculate this change in entropy. So first we calculate the S final. So your final entropy, basically total volume, okay, so it's let's say V, and the number of moles. So now N is basically when we allow the mix, the total number of number of moles is N1 plus N2. So this is basically 2 plus 3 is equals to 5. Okay, right. So then your S final, so this is basically NR, so 5 times R, so 5 times R ln V, okay, so ln V, this is the total volume, okay. And what about the S initial? So initially they have a difference, so delta S1, so S1 plus S2, basically SA, okay, and SB. Okay. So if I go to the last page, so yeah, so this is the problem number 1. So these are the information, right? So what about SA? So SA is basically your N1 times R ln V1 plus N2 and SB N2 moles, okay, so N2 times R ln V2, okay, the volume is V, so total volume is V1 plus V2, right, and your S final is this is the total volume V, okay. So this, how do I get this? So this is basically, you know that so your formula is basically du actually TdS minus PdV, right, okay. So since the du is 0, okay, so this is basically ds, so no, sorry, here is that TdS is basically nr over V dV, right, sorry, nr over V, so we use ideal gas equation, so PV equals to RT nRT, right, and that's how I integrate this, okay. So this is basically sorry, P over T nr over V, right, so this one, so dF equals to nr over V dV. So integrate once we get a ln V, right. So the total V is basically N1 plus N2 times, so V1 plus V2, so this is basically so V1 is N1 times V, okay. So if we integrate this, what about SA? So this is basically N1R integrate of N1V to N1 plus N2 times V, okay. So that is basically change, okay, so delta S, okay, and plus, so this is delta SA, this is the change in entropy. So now if we calculate the change in entropy, so this is basically final minus initial, okay. So that's why I just put in N1 plus N2 times V, okay. Okay, all right. So this is basically delta S, okay, so this is delta S A dV by V, the change in volume, plus N2R ln, sorry, integrate over N2V to N1 plus N2 times V dV by V, okay. So this is basically, so your N1 is 2 mole, right, so 2R ln, right, so 2 plus 3 over 2, right, plus in this case 3R, right, so because N1 2, okay, so this is a O2 gas and N2 is 3, this is H2 gas 3 mole, and this is 3R ln, again this is 2 plus 3 over 3, right. So if we add these two, okay, and we know what is the values of R, so R is basically 8.314 joule per mole per Kelvin. So this is basically gives us that 19.35, okay, joule per mole per Kelvin. Okay, right. So this is the answer. Okay, so let's check the options. Okay, so yeah, so option A is correct, right? So 19.35. Yeah, so far any question or any doubts? Hey Ankit da, hey Ankit da, Ankit da, problem হবে না তো? Okay, so any doubt? Okay, all right. So if it seems there is no more questions, so I'm going to the next one. So in the problem 2, this is exactly again the similar type of problem. So two globes, okay, contain oxygen gas of 3 moles, okay, and a 5 moles, okay, at same temperatures. So a valve connecting the two globes, okay, is opened and the gas allowed to mix. So here both are oxygen gas, okay. So the container A, let's say container B, and both are O2 gas. Okay, and a valve is connecting these two. So now if we, so this is 3 mole and this one again let's say 2 mole. So now we open the valve, okay, and allowing them to mix, okay. Since they are both the same gas, okay, in the container A and container B, so if it mix, it does not change the entropy, right? Because if you know the Gibbs paradox, okay, so the Gibbs paradox, right? So this is known as Gibbs paradox, okay. So if both gas are same, there is a no change in entropy. So no change in entropy if they are same type, okay. So if they are same type, okay. So only only the way to calculate the change in entropy if they are different type of gases. So if they are same type of gas, okay, so then the change in entropy when we allow to mix to, okay, by open the valve, okay, so the change in entropy remains 0, okay. So only non-zero value gives when you mix two different type of gas, okay. So be careful. And that is already known, is famous by Gibbs paradox, okay. So that means in this case the answer is easy, so 0, right? Option C, right? So if we mix this, so in this context I will discuss some things that, so if we mix, let's say two different gas, okay, so just like problem number 1, so if we mix two different gas, let's say N1 mole of type 1 gas, let's say, okay, where the volume is V1, and N2 mole of type 2 okay, gas or the volume is V2. So this V1 is V2 is the volume, okay, and you know that the V1 over V2 is basically N1 over N2, okay, right, and they are basically two globes, okay, or two containers, okay. Now you remove the valve, okay, that is connecting the two containers, okay, and allow to diffuse, okay. So gases to diffuse each other, okay, but they don't interact, okay, and reach a equilibrium state, right. So same, so this equal because same P and T, okay. So pressure and temperatures are equal, so that's why V1 by V2 is N1 by N2, because we use PV equals to RT, okay, ideal gas, okay. So kind of ideal gas, no interactions, okay. So after mixing, okay, they reach a equilibrium state, they are not interacting, okay, so not interacting, okay, so they reach a equilibrium state, okay, so they reach a equilibrium state, okay. So if the gases are different, okay, then the change in entropy, so if the gases are different, okay, so then the change in entropy okay, so basically delta S is delta S final minus delta S initial, okay. So in the delta S final, so their total N is N1 plus N2, right. So this is basically N1 N R Ln total volume is V, and V is V1 plus V2, right, minus the initial one, the first one is N1 R Ln V1 plus, so this entropy is additive, so N2 R Ln V2, right, in doubt. Since the entropy is additive, so we just add this two, okay, so N1 R plus Ln V1 and N2 R Ln V2, okay, and this is the basically your initial entropy, and the final one is basically total N, because now basically they are only one container, okay, so there is no separation, so, right? So there is no diaphragm, okay, so that's separate between two, so it's only one, so it's NR Ln V, okay, total volume V and total number of moles is N1 plus N2. Right? So after simplifying, we can rewrite this. So this is delta S is basically your minus NR, okay, so F ln F, okay, or let's say X ln X plus 1 minus X ln 1 minus X, right. So X is basically, so where X is basically your N1 over N2, sorry, N1 over N or V1 over V, that is equal because same pressure and same temperatures, okay. Okay, so that's why N1 over N and V1 over V is basically X, okay, I define a variables, okay, and your change in entropy is become simple, okay. Right, right, okay, fine. So yeah, so far any question? Okay, so it seems there is no more question. So if it's a special case where when x equals to half, right? So that means both are same. Okay, A and B. Then the entropy is maximum. Okay. So basically, if we plot this, okay, so x can have a 1 maximum value and minimum one is 0. Okay, but in the case when x equals to half, so the change in entropy delta S is basically your NR, and we put x equals to half, so this ln half is negative, so NR ln 2, right? So because x and 1 minus x is also half, right? So this is your maximum entropy, okay, NR ln 2. So if you plot this, okay, so if you plot this where this is 1 and this is 0, okay, so your entropy is maximums when in change in entropy, so this is basically your delta S, and the change in entropy maximum when right, when this is half, when x is half, okay, and this value is basically NR ln 2, okay, if the number of moles is n, total number of moles, so NR ln 2, right? So this is the maximum entropy, and the change in entropy through the x, okay, is in the same, okay. So when x is 1, change in entropy 0, when x is 0, again change in entropy 0, but is maximum when x equals to half. Okay. But if we bring into the context the two masses of same kind of gas, they will also mix, but the change in entropy is it's 0, right? If the same kind, okay. So if they, so I'm writing again, okay. So if the same kind, okay, then they would also mix, okay, but there would be no increase in entropy, but there so but there would be no increase okay, but there will be no increase in entropy. So this is basically the Gibbs paradox. So this is basically Gibbs paradox, okay. Okay, all right. So now I'm going back to the problems. Okay. Yeah. So this is due to the Gibbs paradox. So the change in entropy is 0. Okay, because both are oxygens. So now go to the problem number 3. Okay. So in problem 3, it's basically two bodies of equal mass and thermal capacity is 0.8 joule per Kelvin. So basically the capacity, basically heat capacity, so thermal capacity is C, is 0.8 okay, joule per Kelvin. Okay, are at temperature 100 Kelvin and 200 Kelvin. Okay, so basically your T1 is 100 Kelvin and T2 is 200 Kelvin. Okay. they attain the same temperature on being placed in a direct thermal contact. So when we put into the thermal contact, so they attain at a final same temperatures. Okay, that is basically TF is the final temperature. Okay, and calculate the change in entropy. Okay, right. So how to calculate the change in entropy? So two bodies initially have a different temperatures, right? So this is, let's say, A body T1 temperatures, and this is a B body have T2 temperatures. Now we put a thermal contact. So now if we put a thermal contact, okay, then what is the change in entropy? Okay, so we'll go back to the last page, okay, where I solved this. So this is problem number 3. Yeah, so any suggestion how to compute this? Okay, so what is the change in entropy of the first body? Let's say A. Okay, so I denoted this is the first A and this is the B body. So what is the change in entropy? Delta S1. So the first to calculate the common temperature. Okay, so what is the final temperatures? So the final temperature TF is basically T1 plus T2 over 2. So this is basically 100 plus 200 over 2 is 150, right, Kelvin. Right. And entropy, now if you calculate the entropy change in the first body when the changes 100 to 150 final temperature, right? So the change in entropy, because they reach a common temperature TF, okay, when they are in the thermal contact. Okay. So now I have to calculate first the change in entropy of the first body. So change in entropy of first body. Okay. So this is basically delta S1. This C times, so this is CDT, right? So dq is basically CDT, CDT, okay, and dq is TdS equals to CDT. So as C is the thermal capacity or heat capacity, so this ds is C over T dt. Okay, so C times dt over T, and your temperature changes. Okay, the first body A. Okay, so this 100, because the temperature of the A body 100 Kelvin. Okay, and your final temperature is 150. Okay, so this is basically C times ln 150 over 100, and the change in entropy for second body, let's say B body. Okay, so basically C times 150 to 200, and that is basically dt over t, this is C times ln 200 over 150, right. So the total change in entropy delta S total is delta S1, delta S2, right. So we compare this, so this one is becomes, now we know that what is the values of C, the C value is already given, so 0.8 joule per Kelvin in the problem, right. So we calculate this, so delta S1 plus delta S2, so delta S2 becomes so delta S1 is 0.324, right, joule per, sorry, this is your entropy, yes exactly, so C and the log is dimensionless, so joule per Kelvin, and this is basically minus 0.230 joule per Kelvin, right. So delta S, then delta S1 plus delta S2, so this is basically 0.324 minus 0.230, which is equals to 0.09, okay, joule per Kelvin. So let's check the options. So 0.09 joule per Kelvin. So this is delta S total. So go back to this problem. So problem number 3, right? Yes, so 0.09, option B is correct, right? Yeah, any question? So basically first we calculate the common temperatures TF, okay, and due to this change in temperatures for first body, okay, so due to the change in temperatures of first body from 100 Kelvin to 150, the common temperatures, okay, what is the change in entropy, you first calculate, and similarly you calculate the second body. So the second body temperatures is changing from higher value to lower value, so that's why the delta is negative for the second body, okay, but the first body is the temperature changing from lower value to higher value, so that's why it's positive, okay, the change in entropy is positive. So when you subtract this, or when you add this, basically so the total change in entropy, it becomes very small, okay, 0.09 joule per Kelvin, okay. Yeah, any question? Okay, so it seems there is no more questions, so then I will move to the next one. So the next problem is basically problem number 4, right? Yes. So the internal energy of a system is given by U, actually AP square V, okay, where A is positive constant, and find the equations of adiabates in wavy plane. So this is basically U is A P square V, okay, and you have to calculate the adiabate. So what is the adiabates process? Okay, so this is problem number 4. So this is U is basically A P square V, okay, and the process, the adiabatic process is basically dq equals to 0, right? So the equations of adiabates then, so dq equals to basically tds, so du is dq minus plus dw in my conventions, and minus dw is basically minus pdv. So dw is minus pdv, right? So this is my conventions, right? Okay. So this is the first law of thermodynamics, right? So this is first law of thermodynamics. So then if dq equals to 0 for adiabatic process, right, so then your du plus pdv is 0, right? So if we choose a convention where dq minus dw and dw is pdv, so again this is true, right? So this is independent of the conventions, okay? So du, when you are writing in terms of dv, so there is no issue, okay, right? So du plus pdv is a consistency. So now u is basically a p square v, so du, so this is basically, the a is a constant, right? So a dv p square plus 2a p dp times v, right? So now he plugged these values here, so this is basically a dv p square plus 2a p, okay, dp plus p dv equals to 0. So this is both are dv, right? So dv over v, so this is basically a p square, sorry, a p times p plus 1, no, this is basically p times ap plus 1, right, dv plus 2ap, okay, and then v dp equals to 0. So this implies that a p plus 1 dv over v plus 2ap dp over p equals to 0, right? Sorry, 1 minute. So 2ap dp, yes. So this is basically your ap, no, there is also ap, sorry, I forgot that. So dv over v, so this is basically 2a dp over ap plus 1, that is the correct. So this implies that ln v plus 2, okay, and this a, when we consider a dp as z, so a dp basically your dz, right, and basically a p equals to z, change of variable, right? So ap equals to z, right, and since a is a constant, so a dp equals to dz. So 2 a dp we replace dz over z ap plus 1, and that is equals to 0. So this is basically, sorry, I have to use there, I have not performed any integrations now. So now if we integrate this, so this is basically ln v plus 2 ln z plus 1 equals to 0. So now we plug this value j in terms of a and p. So ln v plus 2 ln ap plus 1 equals to 0. Right. So basically if we multiply this, so ap plus 1 square, so ap plus 1 square times v equals to some constant. No, this is not 0 because we have to integrate this, so this is a constant. And this is also constant, right? So derivative of this constant becomes 0, right? So there is a constants, and this is also a constant. So that means the equations of, so equation in the PV plane, then this AP plus 1 square times V equals to constants. So let's check the options. Yeah, so the last one, okay, so option D is correct. Right, so AP plus 1 times V equals to constant. So we remove this, okay. So this is the correct options, right? So then the option D is correct. Okay, any question? Right? Okay, so the basic steps is that, so once you know what is the form of U, okay, because the U form is given, right? And so basically use the first law of thermodynamics, okay, so du is basically dq plus dw, right? And you know that for the adiabatic process, so one of the thing is the equations of states and the process, right? So once the process is given, so basically the adiabatic process, I know you know that for the adiabatic process dq equals to 0, right? So then the du is basically related to pdv, right? So this is the equations, right? And once you know the form of u, because this is given, okay, then we can calculate du, okay, in terms of dp and dv, okay, and then from this we just integrate this, we can get a equations, okay, in the PV plane. Okay. So very straightforward, okay. You can calculate from other form of u as well, right, in the same way. Okay, so it seems there is no more questions, so then I'll move to the next one. So the next problem is that okay, so the problem number 5. Okay, so this problem is basically a reversible engine cycle is shown in the following TS diagram, okay, and the efficiency of the engine is given by, yeah, so you have to calculate the efficiency of the engine. Okay. So this is a some diagram in the TS plane, okay, you have to calculate the efficiency. Okay, so what is the efficiency for an engine? Okay, how to define the efficiency? So the efficiency, this is basically eta, it's W over Q in, right? So is it work done? Okay, over Q in, okay, the heat input. Okay, so Q in basically the heat input, right? So now in the TS plane, okay, in which of the, so among these three boundaries, okay, in which direction the heat flow, okay, heat enter to the systems, right? So when you calculate the efficiency of this engine, okay, in the TS plane, so you first calculate the work done, the total work done, okay, and the heat input. That is the definitions of the efficiency. So then we first calculate the work done. So intrinsically, you know that in the TS plane, the area of your engine, basically the diagrams, okay, gives you the work done, right? So the work done W is basically area under the curve, area under the curves. Okay. So bounded by the curves. Okay, so you have to calculate the area, right? Closed area in this. So this is basically you have to calculate the area of this. Okay. So how to calculate the area? Because we know this is a triangle. Okay, and the triangle with what is the length of this? This is basically your S1 and 3S1. This is 2S1. And what is the length of height? Okay, so the vertical length. So this is basically your T1, right? So 2T1 minus T1, and this is 3S1 minus S1, right? So area is basically half times base length 2S1 times T1, right? So this is basically S1 times T1, that is your area. Okay, now what is the heat input Q in? So to calculate this, we just take a ratio. Okay, it gives your gives the efficiency of the engine. Okay, so the Q in is basically heat input, right? And your area is basically, so we can also write, sorry, area is the work done, the area in the TS plane is basically Q out minus Q in, right? So once you know that this area in the TS plane is basically gives you the work done. Okay, so then the Q in is basically W Q out minus W. So Q out and yeah, Q out, no, this is basically Q in minus Q out, Q in minus Q out, QH minus QL. So then this is basically Q out plus W. Okay, if we choose the conventions, okay, the heat is without any conventions. Okay, so both are positives. Okay, Q in and Q out. Okay. So then we know the W is this. Okay, S1 and T1, and what is the Q out? So heat is rejected through this line. Okay, where the temperature is constant. So dq equals to basically TdS, right? So here the temperature is constant in this way, okay, and the entropy changes, so that's why dq it changes. So the delta q or the q out is basically your temperature is T1 times delta S. So delta is basically T1 times 3s1 minus 2s1, right? So 3s1 minus s1, this is 2s1. So therefore your q in is q out, basically T1 s1 plus 2 T1 s1. So this is basically 3 T1 s1, okay, and your W is T1 s1, right? So T1 s1. So which implies that eta is equals to W over Q in. So T1 s1 over 3 T1 s1. This is basically 1/3. Right, this is a 1/3. So that means option A is correct. So remember the area in the inside the curves, okay, is basically work done in the TS plane. Okay. Yeah. So any question or any doubts? So in the TS plane, if you plot the adiabatic curve, isotherms curve, okay, isotherm curve is very simple because isotherm curve means the temperature is constant, right? So this line, okay, so this is isotherm line, okay, but the adiabatic one is where the entropy is constant. So this kind of line is the adiabatic where the entropy is constant, okay, because dq is 0 for the adiabatic process, right? Okay, I'll come into this point, but first, if there are any questions in this point, okay, then you ask, okay, then I will come to this point, okay. Okay, so it seems like there are no questions. Okay, so an isotherm curve and adiabatic isotherm curve and adiabatic curve in the PV plane correspond to the TS plane exactly. So the isotherm curve is very simple. So in the TS plane, so let's say this is S and this one is T in the vertical axis, right? So isotherm is basically temperature constant, right? So dT is 0 for isotherm, right? So that means this is just straight line, okay, the horizontal straight line, okay, in the TS plane. So this is your isotherm. Now for adiabatic is basically so for adiabatic is dq equals to 0, right? So you know that dq is basically TdS, right? So ds is equals to 0, right? So that means the entropy is constant, okay. So this is basically something like this, okay. So this is your adiabatic, okay. What about the values of T? The ds is 0, okay, the variations of entropy is 0, right, because dq equals to TdS, okay. So this is adiabatic and this is isotherm, okay. So this is basically both a straight line. So first the isotherm curve, okay, so this is correspond to the straight line, horizontal straight line. So this is horizontal straight line parallel to S. So this one, and your adiabatic curve, okay, is a horizontal straight line parallel to T axis. Yes, so this option C is correct, right? So okay, it's clear, or any further doubts? Okay, so then if there is no questions, okay, let's wait for 1 more minute. If you have, you can also write in the chat box. So, okay, so let's go to the problem number 7. So in a standard air auto engine, the air intake take place at atmospheric pressure, okay, at 30 degrees centigrade. Before the ignition, the pressure of the combustion chamber, okay, is 16 times the initial pressure. Find the compression ratio if gamma is given. So here gamma is basically Cp over Cp, okay, the ratio of the specific heat at constant volume, at constant pressure and constant volume. So this is given 1.5, right? The values of gamma is given, and yes, so and the pressure is P, yeah, the pressure is basically P2 is 16 times P1, okay, so the pressure is 16 times the initial pressure, okay, so the final pressure is P2 is basically 16 times your initial pressure. Okay, so this 2 is given. So you have to calculate the compression ratio, right? So first of all, what is the Otto cycle, right, or Otto engine? You know about the Otto engines? So the Otto cycle. So let's first discuss about briefly about the Otto cycle. Okay, so basically you have a P plane. Okay, and let's say there is a, so Otto cycle is basically 2 adiabatics, 2 isochoric process. Okay, so that means in the PV plane, so this is an adiabatic, okay, it's very steep, and this is an another adiabatic, and there is a 2 isochoric. So let's use some other color. So isochoric means volume constant, right? So this is basically adiabatic, and this one is isochoric. So adiabatic means that dq is 0, and isochoric means that the volume constants, okay, so dv 0. Right. Okay. So now the which way the heat entered to the system, heat entered to the engine. So the adiabatic, there is no change in heat, right? So only the possible is that in these directions the heat enter, and this way the heat rejected, right? So this is basically QL, heat rejected, and heat enter is QH. Okay, and we marking these two. So this is basically 1, 2. Okay, this is 3, and this is 4. Right. So this is a cycle. Okay, and that is the Otto cycle, right? So it contains 2 adiabatic and 2 isochoric. So we calculate this. Okay, so in this Otto cycle, you have to calculate the compression ratio, right? So the compression ratio R for this cycle, so compression ratio R is basically equals to V1 over V2, right? V1 over V2. Okay. So now this PV1 to P2 V2 is basically follow a adiabatic process. Okay. So in this point, your P1 V1, and this point is your P2 V2. Okay. So then they follow the adiabatic process. So P1 V1 to the power gamma equals to P2 V2 to the power gamma, right? And V1 over V2 for gamma, okay, actually P2 over P1, right? So that is basically, so in the given problem, P2 is 16 times P1, so 16 times P1, right, over P1, so it's basically 16. Okay. So now we know the values of gamma, right? Because the gamma value is given 1.5, the Cp over Cv, right? This is 1.5. So then the V1 over V2 is basically 16 over 1 over gamma 1.5. So this is basically 16 over 2 over 3, and you know that this 16 is basically 4 square, so 2 to the power 4, so 2 to the power 8 over 3, so it's close to 6.35, right? So this is the compression ratio. Okay, so the compression ratio, I think I wrote somewhere, yeah, so R, right? So this is basically R. Okay. So 6.35. Okay, so let's check the options. Okay, yeah, so the option B. So option B is correct. Okay, any question? Okay, so it seems like there is no more question. So then I will move to the next one. So in the problem number 8, so the problem is basically if the compression ratio of a diesel engine, okay, is 15 and fuel cut-off ratio is 3, okay, so then find the efficiency of the engine, right? So there is a fuel cut-off and so it's a diesel engine, right? So the auto engine is kind of a diesel engine, right? So okay, so sorry, so in the diesel engine, how to calculate the efficiency? The efficiency of the diesel engine, so the efficiency eta is basically 1 minus 1 over r to the power gamma minus 1, and there is a fuel cut-off ratio. So this fuel cut-off ratio, fuel okay, so the fuel cut-off ratio it actually 1 minus r to the power gamma minus 1, right, times rho to the power. So fuel cut-off ratio, what is that? Fuel cut-off ratio, rho equal to basically 3. Okay, so what is rho? So rho is basically, okay, I'll discuss later, but so rho equals to 3, right? So this rho to the power gamma minus 1 over gamma times rho minus 1. Okay, so the efficiency of the Otto cycle just previously discussed. Okay, so the basically Otto engine. Okay, so the efficiency of Otto engine. Okay, so this is eta is basically 1 minus r to the power 1 over r to the power gamma minus 1, 1 over r to the power gamma minus 1. But here they are modified some factor. Okay, so this extra factor, so this extra factor is basically modified. Okay, okay, so it's rho to the power gamma minus 1, gamma times rho minus 1. Okay, so this factor is modified from the Otto engine. Okay, okay, any question? Okay, so this is the diesel engine. So this cutoff for a fine fuel cutoff is basically 3 in the diesel engine. Okay, so now plug these values. Okay, and we know the compression ratio is R is basically 15. Okay, so this is compression ratio. Okay, so this is basically 1 minus 1 over so r to the power gamma minus 1. So r to the power, so r is 15 and to the power gamma, so it's basically 0.5. Okay, this is minus 1 times plug these values. Okay, so rho is 3 to the power 1.5 minus 1 over 1.5 times 2. Okay, so once you calculate this, the value becomes 0.6385. Okay, right, so just cross check. So this is times. Okay, so 1.5 times 2, so this becomes 3. Okay. So this is basically r to the power gamma minus 1. So this, okay, sorry, yeah, so this one is correct. So it's basically 15 over half, square root of 15. At the end, the answer is that 0.6385. So basically, you are 63%. So the efficiency eta it's roughly 63%. So this is basically, I mean, it's close to option C, 64%, right? 63.8, so it's nearly close to 60. Sorry, it's 63.85. So it's approximate 64, not 63. So option C is correct, right? Yeah. Any question? Okay, so it seems there is no more questions. So then I will move to the next one. So the compression ratio in a diesel engine is 22. So again the R value is given, the compression ratio is 22. Okay. If the temperature of the fuel before and immediately after the combustion is 647 and 1751 degrees centigrade, right? So your T1 is basically 647 degrees centigrade. So if you just convert into a Kelvin, right? So this is basically 647 plus 243. Okay, wait a minute. So basically around 919. So is very close to 9, so 276. So yeah, so 246 plus 273, right? So 647 plus, yes, so 273 Kelvin. So this is becomes 9 647 plus 2, basically 920, right? And your T2 is basically what is the value? 1751, right? So 1751 plus 273. This is the Kelvin. So 1751 plus 273 is basically 2024 Kelvin, right? Okay. So then So once you know T1 and T2, so you have to calculate, because the eta is contains 1 over r to the power gamma minus 1 times rho to the power gamma minus 1 over gamma times rho minus 1, right? So you first calculate rho. Okay, what is the values of rho? So this is basically fuel cutoff, right? So how to calculate fuel cutoff rho? So this is basically volume after, okay, V3 over V2. So volume, okay, immediately after the combustion, okay, and V2 is the volume before the combustion. Okay, so volume before combustion, okay, and this V3, we take the ratio, okay. So rho equals to basically ratio of these two, okay, V3 over V. So this is basically volume after combustion, right? So how to calculate this V3 over V2? Because this V3 over V2 is exactly T3 over T2, so T2 over T1, okay. So temp is proportional to temperature, right? So from the Charles law, right? So if you know the Charles law, so C is R. So Charles law, it suggests that the V volume is proportional to temperature, right? So that means V3 over V2 is basically, okay, just name is that. So let's say this is put V2 and this is V1, okay, and this is your V2, this is your V1, and this is basically T2 over T1. Right. So then, so this is again the T2 is basically V2 is volume after combustion. So T2 is basically the temperature after combustion, right? And V1 is the volume before combustion, is basically the temperature before combustion, right? So this basically 2024 over 920, right? So once you know this, okay, what is the value this? So 2024 divided by, sorry, divided over 920, right? So it's basically 2.2, right? So this is the rho value, right? So the values of rho is basically 2.2. So once you know the rho value and the gamma value is provided 1.4, so you can calculate it, right? So just plug this value. So your eta equals to 1 minus 1 over r. So what the values of r is given 22 to the power 0.4 times 2.2 1.4 minus 1 over 2.2, sorry, 1.4 times 1.2, right? So if you calculate this, is basically 1.4. So if you calculate this, so the number becomes 0.6515, 0.6515. So this, the eta is basically 65%, right? So the option A, right? So the option A is correct, okay? So the values of eta is basically 65%. Okay, this is the efficiency. Okay, so if you have any questions, you can ask. Okay, or any doubts. Okay, if you have any questions, you write in the chat box. Okay, I'm coming into 2 minutes. Okay, so any questions for this? Okay, so there is a no question. Okay, so then I will move to the next one. So the last problem. So the last problem, calculate the efficiency eta of an engine, okay, with an ideal gas, okay, operating in the cycle as shown in figure below. So you have to calculate the efficiency, right? So for this cycle, right? So C2A, okay, is a volume compression, okay, and A to B is basically pressure increasing at a constant volumes, and there is some adiabatic process. Right? So one is the constant pressure, constant volume, and adiabatic process. So isobaric. So this is basically isobaric, and this is isochoric, right? And this is adiabatic. Okay. So this is adiabatic. So dq equals to 0. Here dp equals to 0. Here dv equals to 0. Okay, so no change in volume, right? So first we calculate again the efficiency. Eta is defined W over Q in, right? So first we calculate the work done and the heat input, right? So this is heat input, okay. So where the Q in is heat input, right? So how to compute this? So this is basically CV over R, okay, right? And then you are basically for this point, so this is Q in, right? So in this process, okay. So where dV equals to 0, So P at this point is basically your 3 P naught V. So this is the volume is V naught. So V naught and the change in pressure 3 P naught minus P naught, right? So this is your heat input QAB, right? So this is your heat input Q in, okay, and heat out in this, because there is no exchange in heat in the adiabatic process, right? So it's dQ0. So Q in through the AB. So Q in basically QAB, and Q out is reject heat. Okay, so it's QCA. So then how to calculate this? So Cv over R, and then is the PV, right? Okay. Okay, all right. So then this is basically 2 P naught V, okay, and your Cv is basically R over gamma minus 1, right? So it's constant volume Cv, right? Because the heat enter through the AB process, okay, A to B, okay, so this is constant volume, so Cv is R over gamma minus 1, so this is basically gamma minus 1, okay, so that is your Q in. So next you have to calculate the work done, okay. So how to calculate the work done? So the work done W is basically 3 process, W A to B plus W B to C plus W C to A, WCA, right? So work done for W A to B, okay, is basically at constant from A to B, right? So this is basically at constant volume, right? So at constant volume there is a no work done, right? So W is basically P dV, right? So if dV 0, so this is 0, and B to C, the work done is basically, you know that the for adiabatic process, right? So for adiabatic process, work done is P1 V1. So your initial states is 3 P naught times V naught, right? For adiabatic process, the work done W is P1 V1 minus P2 V2 over gamma minus 1, right? For the adiabatic process, okay. So this is basically 3 P naught V naught minus your P2 V2 is basically C point, so 2 V naught and P naught. The pressure is P naught, okay, and the volume is also 2 V naught, and divided by gamma minus 1 plus WCA. So at constant pressure, right? So this is not a problem. So it's P naught is times dV. So dV is basically yeah, so 2 V naught minus V naught, right? So then your W, so this W equals to this P naught V naught 2 minus gamma over gamma minus 1, okay. This is basically your W value, and the Q in basically 2 P naught V over gamma minus 1, 2 P naught V over gamma minus 1. So this implies that eta is W over Q in, so 2 P naught V over W, so this is basically P naught V times 2 minus gamma over 2 P naught V, right? So this P naught V cancel, so it's 2 minus gamma over 2. So this is your efficiency, right? So now what is the values of gamma? So gamma is, the values of gamma is given 1.4, right? So the eta value is basically 2 minus 1.4 by 2, so it's 0.6 by 2, right? So it's 0.3. The option C is correct. Okay. Any question? So first we calculate the the area. First we calculate the work done. Okay, W for the three process A to B, B to C, C to A. Okay, and A to B, since it is constant volumes. Okay, so its work done is 0, and B to C is adiabatic. We know how to calculate the work done for the adiabatic process and also for the isobaric process. So is P constant, so it's just a PD. Okay, volume changes. That's why its work done is positives. Okay, and we add up this. Okay. So once you calculate the work done, the next part is to calculate the heat input. Okay, and the heat input through the A to B process. Okay, this is basically an isochoric process where dV equals to 0. Okay, and Q is basically your CV over R times PV, right? Right, because CV dt, right? So now your dt is basically PV over R, right? So you know that the Q is basically dQ is CV times dt. So it's dt we can change is basically R is PV equals to RT, right? So T is PV over R, right? So at constant volume, right? So this dt is basically at constant volume, so V over R dp, right? So that's why is V is basically constant V naught, and dp your change is basically P2 minus P1, right? So this 3 P naught minus P naught is 2 P naught, right? And then CV you know, and the V naught R. Okay, so once you replace this CV to R over gamma minus 1, okay, then it's R cancel. Okay, so it's only gamma minus 1 left in the denominator, and we calculate this. So once you know the W and Q in for a given cycle, so you can calculate the efficiency eta is W over Q in. Okay, so use the standard formula. Okay, the definitions. Okay, and then just plug the values of the gamma. Okay, we get the numerical values of eta. Okay, so I hope you for given another cycles. Okay, you are easy to calculate. Okay, using this methods. Okay, it is easy to calculate the efficiency. Okay, for a given cycle. So. Okay, so is there any other questions? Okay, so if not, then I actually discuss something, some difference between the TS plane and PV planes. Okay, how the one diagrams, okay, in the PV planes translate into the TS plane. Okay, so let's say first consider the EG1 is the Carnot cycle, right? So the Carnot cycle. So this Carnot cycle is basically in the PV plane. So PV. So there is a two adiabatics, two isotherms, right? This is, let's say, A. Let's say 1, 2, 3, 4, right? Okay. So 1 to 2 is the isotherm, and these two are the adiabatics. So adiabatics, right? So adiabatic. Okay. So now if we convert into a TS plane, so how it looks like in the TS plane? So first 1 to 2, right? So 1 to 2 is basically isotherm process, right? Okay. So isotherm means constant temperature. So in the TS planes, so this is 1, 2, okay, constant temperatures, and then 2 to 3 is adiabatic. So that means constant entropy. Okay. And constant entropy, right? Adiabatics. And again 3 to 4, again isotherm. So 3 to 4, and again 4 to 1 adiabatics. Right. So this is 4 to 1, right? Again constant entropy, right? Okay. So this is basically a rectangle. And if we closely plot this, so this is basically a rectangle. Okay, in the TS plane. So it's basically a rectangle. Okay, in the TS plane. Okay. What about the other kind of cycles? Let's say for Otto cycle, second one, Otto cycle. Okay. So the Otto cycle is basically in your PV plane. Okay, 2 adiabatic and 2 isochoric, right? So let's say this one is a one of the adiabatic, and this is another one. Okay, and there is a 2 isochoric. Okay, so this is basically adiabatic. Okay, this is isochoric, right? It's a constant volume, and this is dq equals to 0. This is dv equals to 0. Okay, so if we translate this into TS plane, okay, so in this plane, how it's look like? So first let's say put a number 1, 2, 3, 4, right? So 1 to 2, 2 to 3, 3 to 4, 4 to 1. Okay, and in the TS plane, so first 1 to 2 is adiabatic, right? So it's a constant entropy. So this is basically straight line. Okay, and then is 2 to 3 isochoric, right? So 2 to 3 is a constant volume. Now how the constant volumes look like in the TS plane? Right? The constant volume it looks like in the TS plane like this. Okay, and so this is 1 to 2, 2 to 3, and again 3 to 4 isotherm is a sorry, adiabatic, so is a entropy constant. Okay, and again 4 to 1 is a constant volume. So constant volume in the TS plane looks like this. So, right. So that means so this is 4. Right. So 1 to 2, 2 to 3, 3 to 4, 4 to 1. Right. Okay. So something like looks like this. Okay. So this is a isochronic process in the TS plane 2 to 3. Okay. Okay. Right. So hope it's clear. Okay. I mean, how to change from one plane to other planes. Okay. Process by process. Okay. Okay. So is there any questions and doubts further? If you have, then please ask. Okay. So the next session, I think March 23, so March 30, right? Okay. So this is the next session. So, okay, so okay, it seems that there is no more questions. So I stop the session. Yeah. Okay. So see you the next Sunday at 4 p.m. Okay. Thank you. Bye bye.